Okay, hi, so welcome to the video where we're going to go through the AQA 2015 paper for Unit 2 Physics. This is the higher paper, so if you're doing foundation, some of this won't apply to you. But as per usual, we're going to go through one by one, and if at any point you're struggling to keep up, please feel free to pause the video, rewind, and go at your own pace, okay? But we're going to go straight on with question 1. Alright, now question 1 says that figure 1 shows the current potential difference graph for 3 wires, and those wires are A, B, and C. And 1A says, using figure 1, how can you tell that the temperature of each wire is constant? Alright, now you need to know that at constant temperature, you have constant resistance, right? Because resistance varies with temperature. And now from this graph, you can see that all these lines are straight lines. And so we can see that current is directly proportional to the PD, which tells you constant resistance, okay, which equals constant resistance, and that will tell you constant temperature. All right, now that's all good for 1 mark. So part 2, it says, which one of the wires has the greatest resistance? Now let's go and have a look at the graph. Now you'll remember that voltage is equal to current times resistance, all right? And so which one of these has the greatest resistance is the one where the potential difference increase doesn't increase the current as much as the rest of them. So at a high value of resistance, okay, we're going to get a high value of our voltage, but not giving us a very high value of our current, right? Whereas if the resistance was low, in order to get a high voltage, so let's say, for example, here, in order to get a high voltage, you would need a high current. And so you're looking at one of the top graphs, whereas if the resistance was high, to get a high voltage, you wouldn't need a very high current. And so it's going to be C, okay? So our graph is going to be C. And the reason will be that for same potential difference, okay? So going up here, you can see from the same potential difference where I've marked these crosses, the current is the lowest in C. Current, smallest in C. All right. Okay, so let's move on. So we've got 1B. A student measured the resistance of 4 wires, and table 1 shows the resistance of and other data about each of the 4 wires J, K, L, and M. Alright, now B part 1 tells us that the last column of the table should include the unit for resistance. What is the unit of resistance? Now the units for resistance are the ohms. Okay, so I'm going to say the ohm, and just in case you wanted the symbol in brackets, there we go, that is the symbol for the ohm. Now B part 2, it says the resistance of a wire depends on many factors. Look at table 1. Which 2 wires, J, K, L, and M, show that the resistance of a wire depends on the length of the wire? And so what we're looking at is 2 wires which are similar, but that differ only in length. And by looking, obviously it's not going to be M, so I can discount that straight away because that's made of a different material. So J, K, and L are made of copper, and let's have a look here. In diameter, we've got a different diameter there. So I'm going to say it's not going to be J either. But the diameter is the same in K and L. The only thing that's different is the length of the wire. And you can see that the resistance has actually changed. So the 2 wires I'm going to label are K and L, because the only difference between those two is the length, right? And that will be the reason I'm going to give the only difference, so about that, between them is the length. All right, let's move on. B part 3, it says a student looked at the data in table 1 and wrote this conclusion. The resistance of a wire depends on the type of metal from which the wire is made of. Okay? Underneath it says the student could not be certain that her conclusion is true for all types of metals. Suggest what extra data is needed for the student to be more certain that the conclusion is correct. Well, from our table, we only have data, okay, oh, sorry about that. We only have data in this table on ignore that black screen. There we go. We only have data in the table on 2 different types of metals, and so that's not enough to say that the type of metal will change the resistance for every type of metal. So what we need is more data on different types of metals. Alright, now this is a 1-mark question, and that is all we need to write. So 1C, it says the resistance of a wire can be calculated using readings from an ammeter and a voltmeter. Complete figure 2 by drawing a voltmeter in the correct position in the circuit. Okay, use the correct symbol for a voltmeter. So you should know that a voltmeter needs to be placed in parallel with what it's measuring, and we are going to be measuring across the wire, and the wire is labelled down here. So we need to put in parallel a voltmeter. Okay, and a voltmeter has the symbol, which is very easy to remember, of V, and putting that in parallel with the wire is good enough for that 1 mark. Okay, let's move on. 1C, we have said that in a circuit diagram, a wire can be represented by the symbol for a resistor. In the box below, draw the circuit symbol for a resistor. Okay, and this is a really plain, easy one. A resistor is just like so. It's just a box with a wire on either side. Okay, so it's just a rectangle, and that is it. And that's the end of question 1. Alright, so question 2 now. In part A, we are told over 100 years ago, scientists thought the atom was like a plum pudding. And figure 3 shows a plum pudding model of the atom, right? So we've got a nice diagram there. Scientists knew that an atom has negatively charged particles. They also knew that they had no overall charge. What did the scientists conclude about the charge on the pudding part, right? Well, if we have negatively charged particles but no overall charge, we need to balance that out with positively charged particles, or at least a positive charge in this case, because we're not told that it's particles. So they concluded that the pudding was equally positively charged. Right, because that will cancel out the negative charge on the particles, obviously, which we now know are electrons. So we carry on. 2 scientists, Rutherford and Marsden, devised an experiment to investigate the plum pudding model of the atom. The experiment involved firing alpha particles at a thin sheet of gold, and they measured how many alpha particles were scattered. Using the plum pudding model, the scientists predicted only a few alpha particles would be scattered by more than 4 degrees. Over several months, more than 100,000 measurements were made. The results from this experiment caused the plum pudding model to be replaced by a new model of the atom. Alright, now it says explain why. So, the first thing to note is that they predicted only a few would be scattered more than 4 degrees. In reality, lots of them were scattered by more than 4 degrees. So, found that many alpha particles were scattered more than 4 degrees. Okay, this could not be explained by the plum pudding model, and that's why they replaced it. Okay, so could not be explained by plum pudding model. Alright, so the plum pudding model could not explain the results that they obtained. And so that's more than enough for 2 marks. Let's move on. We've got part 2. Suggest one reason why other scientists thought this experiment provided valid, okay, let's underline that, valid evidence for a new model of the atom. Now the most obvious one, if we go back up to the question, you can see that it says over several months, more than 100,000 measurements were made. Now we are told obviously to never just take an experiment and take 1 reading. We're told normally to repeat and take 3. Now imagine taking 100,000 measurements. Now that is quite drastic. So 100,000 measurements is enough for results to to be valid. Okay? Because this really will get rid of any random errors or anomalous results because you've taken so many readings. Okay, so 2C, it says we're going to be assessed on our English. Okay. Now it says describe the model now used for the structure of the atom, and we should give detail on the individual particles that make up the atom and the relative masses and relative charges of the particles. And it says definitely do not include a diagram in your answer. So if you do include a diagram, they will actually deduct marks. All right, now I'm not going to write in full sentences because it will take too much time for this video. But I will write all the main points that you need to get down, but you do need to write in full sentences and make sure that everything is in order. Okay, so first of all, it says give details about the individual particles. So now I'm going to say that an atom is made up of protons, neutrons, and electrons. Okay, protons have a relative charge of +1. Okay, neutrons have a relative charge of 0. Electrons have a relative charge of -1. All right. We also need to talk about the masses. The protons have a relative mass of 1. Neutrons have a relative mass of 1. There we go. Electrons. Let's rewrite that because you can't really read it. Electrons have a relative mass of almost 0. Right, and I'm going to put in brackets here about 1/2000. If you're being slightly more precise, it's about 1/1840, but it's almost 0. Okay, in calculations in GCSE, we do treat it as 0, but it's actually it does have a mass. It's just not very big. Okay, and then finally the arrangement. I'm going to say that protons and neutrons are found in the center of the atom, in the nucleus. Okay, electrons are found in shells or energy levels surrounding the nucleus. Okay, and that will be more than enough to get you all the marks, okay, because I've mentioned the charge, I've mentioned the mass, and I've mentioned where you find all 3 particles. Okay, put that into full sentences and that is definitely 6 marks. Okay, so question 3 now. We are told that many countries use nuclear power stations to generate electricity. Nuclear power stations use the process of nuclear fission to release energy. Part 1, it says, what is nuclear fission? Now, fission is the opposite of fusion. Fission is where we split up a nucleus. So fission is the splitting of an atomic nucleus. Okay, and I'll put in brackets here multiple nuclei. Alright, now part 2. Plutonium-239 is one substance used as a fuel in a nuclear reactor. For nuclear fission to happen, the nucleus must absorb a particle. What type of particle must be absorbed? And now, no explanation needed here, it's 1 mark, is a neutron. Alright, you should remember that. A neutron goes in, splits the nucleus, and more neutrons are released. Okay, in B, it says that fusion also releases energy. Nuclear fusion happens at a very high temperature. Very true. A high temperature is needed to overcome the repulsion force between the nuclei. Why is there a repulsion force between the nuclei of atoms? Now, we mentioned previously that the nucleus contains neutrons and protons. Now, the neutrons are not charged, but the protons are positively charged. And so, therefore, a nucleus is positively charged. So, you can say that all nuclei are positively charged. Okay, and like charges repel. Like so. Okay? Alright, where does nuclear fusion happen naturally? It happens in a star. Okay, and if we're being more specific, you can say that it happens in a main sequence star, because there are other stages in a star's life cycle where it's not going to be happening. Okay, so we move on. 3C. In 1991, scientists produced the first controlled release of energy from an experimental nuclear fusion reactor. This was achieved by fusing the hydrogen isotopes deuterium and tritium. Deuterium is naturally occurring and can easily be extracted from seawater. Tritium can be produced from lithium. Lithium is also found in seawater. Table 2 gives the energy released from 1 kilogram of fusion fuel and from 1 kilogram of fission fuel. So, we have the numbers here. In 3C, it says, suggest 2 advantages of the fuel used in a fusion reactor compared with plutonium and the other substances used as fuel in a fission reactor. Okay, so looking at the table, the first thing I can see is that the fusion fuel releases more energy than the fission fuel. Okay, so the first thing I'd say is releases more energy per kilogram. All right, and it does, and so that is fine. So what else would be an advantage? Well, there are a few. It tells you in the question that tritium and deuterium can both be extracted from seawater. That is an abundant resource, and so there's a lot of it available. So I can say that the fuel is available in large quantities. Okay, and that's more than enough for 2 marks. You could have also mentioned the fact that you don't produce a lot of radioactive waste, which you certainly do when you use something like plutonium. So that would be another advantage that you could have put. Alright, so for part 2, it says some scientists think that by the year 2050, a nuclear fusion power station capable of generating electricity on a large scale will have been developed. Suggest 1 important consequence of developing nuclear fusion power stations to generate electricity. Now, there are loads of ways of wording this. It's only a 1-mark question, but if we could produce produce energy from nuclear fusion, and the fuel for fusion was available in seawater, that means we've now got a massively abundant supply of energy. Obviously, you hear on the news all the time that the supplies of energy are going down and down in terms of fossil fuels and everything else. And so that would be a really good thing. So it would allow more electricity to be generated. From an abundant source. Okay, and that's more than enough. You could have also said that it reduces the amount of other fuels that we have to use. You could have said that there is less pollution going to be produced from generating electricity. All of those would have been really valid points. All right, 3D. Tritium is radioactive. After 36 years, only 10 grams of tritium remains from an original sample of 80 grams. Calculate the half-life of tritium and show how you worked out your answer. Okay, now remember the half-life is the amount of time it takes for the amount of the radioactive substance to drop by a half, right? And so the first half-life, if I've got 80 grams, okay, and I times that by a half, I will end up with 40 grams, okay? And that's after 1 half-life. So I'll put 1 there, all right? Now, the second half-life is going to be, well, from 40 grams times a half will give me 20 grams. Okay, that's the second half-life. Now the third half-life, you can imagine, is going to be 20 times a half would give me 10 grams. Okay, and 10 grams is the amount we want. So how many half-lives has it taken? 1, 2, 3. Okay, so 36 years, which is how long that's taken in total, equals 3 half-lives. Alright, so what's one half-life? Well, we divide both sides by 3. Therefore, divided by 3, 12 years, because the time remains constant, is equal to 1 half-life. Alright, so the time taken for the half-life is 12 years. Alright, and that is the end of question 3D. So question 4 now, it says that a car driver sees the traffic in front is not moving and so he brakes to stop the car. The stopping distance of a car is the thinking distance plus the braking distance. That's true, we've learnt that before. What is meant by the braking distance? Well, the braking distance is basically how far the car travels when the brakes are applied. So, it's the distance travelled after brakes applied until the car stops. Alright, and that is the braking distance. Part 2, it says the braking distance of a car depends on the speed of the car and the braking force. State one other factor that affects the braking distance. Now, there are many. One that I'm going to say is the condition of the tyres. Condition of tyres. Because if your tyres have barely got any grip, then the braking distance is going to be increased. You can also think about the condition of the brakes. If you've got worn brakes, that's going to affect it. If the road is icy or wet, that's going to cause the car to slide and it's going to increase the braking distance. If the surface of the road is really smooth or it's really gravelly, a smooth tarmacked road is going to provide a lot more grip, whereas if it's gravelly, the stones slide about and you don't get as much friction from the road to stop the car. Also, the mass of the car or the weight of the car is going to affect how quickly you can stop as well. Okay, all of those things would affect the braking distance. How does the braking force needed to stop a car in a particular distance depend on the speed of the car? Alright, so if you think about it, if the speed is greater, you're going to have to apply more force to stop the car in a particular distance because you'll need an increased acceleration backwards, okay, or a deceleration. So, the braking force required is greater at greater speeds. Okay, and it's only a 1 mark question, so we don't need to explain that. 4B. Figure 4 shows the distance time graph for the car in the 10 seconds before the driver applies the brakes. Use figure 4 to calculate the maximum speed the car was travelling at. Show clearly how we worked out the answer. Alright, now what we need to do for this question is we need to work out the speed from the graph. Now, if you have a look, the steepest point on the graph is going to be when the car is travelling the fastest. And the steepest point is here at the end, because look, it's a straight line at the end. Not my drawing, but you can see where I'm pointing at. The straight line is steeper than the curve down here, okay? Because if I was to draw a tangent at the curve here, it would not be as steep as the straight line at the top. So, what I'm going to do is I'm going to take 2 points, which I can easily read off, and work out the gradient of the line from those 2 points. The points I'm going to pick are going to be whole number points, and that's going to be here, okay? And it's also going to be here, all right? There we go, zoomed in so you can see it a little better. So, those are my 2 points. This first one, okay, well, what is the distance in meters? The distance in meters, well, it's 4 out of 5 between 150 and 175. And so that means that each square is 5, and that makes 4. 5s are 20 on top of 150, so that's 170. Okay, and where is it on the x-axis? And that's 10 seconds. Okay, now this point here, it's on 125, and 8 seconds. Okay? Now for the gradient of the graph, it's the change in y over the change in x. And the y-axis is 170 and 125. Okay? So I'm going to do 170 minus 125 divided by 10 minus 8. 170 minus 125 will give me a total of 45. 10 minus 8 will give me 2. And so I've got 45 divided by 2 equals 22.5. And that's 22.5 what? Well, the distance is in meters and the time is in seconds. So it's 22.5 meters per second. And so there we go. I'll come down and say 22.5. And they've given me the units. That's in meters per second. Okay? So that's the end of that. If we'd have worked it out down the bottom, we could not have got all the marks. If we had have just assumed that this was a straight line and done the top and the bottom, we wouldn't have got all the marks either, because this bottom part of the graph is a curve. We have to take the maximum speed, which is when it's steepest, which is this part of the top. All right? And so that's how we get our answer. Moving on. We've got 4C. The car did not stop in time. It collided with the stationary car in front, joining the two cars together after it collided, obviously. Figure 5 shows both cars just before and just after the collision. The momentum of the two cars was conserved. What is meant by the statement, momentum is conserved? When we say conserved, it means the total momentum before is equal to the total momentum afterwards. So total momentum before collision equals total momentum after. Alright, now 4C part 2, it tells us to calculate the velocity of the two joined cars immediately after the collision. Now what I'm going to do is use the law that I've just stated. Total momentum before equals total momentum after. All right. So I'm going to have a look first at before the collision. Now before the collision, you've got the car on the left, which is of mass 1500 kilos and of velocity 8 meters per second. Right. So I'm going to say that momentum is equal to mass times velocity. Right. So momentum is equal to 1500 times by 8. Okay, and so you do 1500 times 8, and that will give you a total of 12,000 kilogram meters per second. Now, how about the other car? Well, the other car is traveling at a velocity of exactly no meters per second. So if you did momentum equals 900 kilograms times by the velocity, 0, you would get an answer of 0. And so the total momentum before the collision is only the momentum of the car on the left, because that's the only one moving. All right. So that is before the collision. Now after the collision, I'm going to do on this side, and I'm going to say that total momentum must be conserved, right? So I'm going to use the same equation, but the momentum is conserved. So I now know the momentum is 12,000. That is equal to the mass times the velocity. Well, I want the velocity. Do I know the mass? Yes, I do, because they're moving together. They have a total mass of 1500 plus 900 equals 2400 kilograms. All right, so I replace mass with 2400. All right, and that is times by the velocity. I now rearrange to get velocity on its own by dividing by the mass. So I get 12,000 divided by 2400 is going to give me an answer of 5 meters per second. All right, and so that is my answer, 5. Okay, so let's move on to the next part. We've got question 4D. It says, since 1965, all cars manufactured for use in the UK must have seat belts. It's safer for a driver to be wearing a seatbelt compared with not wearing a seatbelt if the car is involved in a collision. Explain why. Okay, and so what we need to think about is, how is a seatbelt designed? Well, a seatbelt is designed so that it stretches, okay? So the stretch in the seatbelt allows driver to move. Okay, why is that important? Well, because if during a collision the driver is allowed to move, that means that the impact time of the driver, the impact time on the driver is going to be greater. So we have a greater duration of impact. Higher impact time. Sorry for that handwriting there. So higher impact time. All right. Okay. So if the driver was allowed to just carry on moving and hit the windshield would either suddenly stop the driver or the driver would fly through the windshield, right? So if driver hit windshield, impact time would be reduced. Okay. Now, one thing I want to say at the end of that is that is for the same momentum, okay? For the same change in momentum, because the driver is going to have the momentum change exactly the same depending on whether he's wearing a seatbelt or not, because the car has still crashed. That wearing a seatbelt doesn't make any difference to the fact that the car has crashed. So momentum change is the same. Okay, and then what I'm going to say is that force is equal to momentum divided by impact time. And therefore, greater impact time for same change in momentum means the force exerted on the driver is reduced. Okay, and that's more than enough to get the 4 marks. So you need to say the fact that the seatbelt will stretch increases the impact time for the same change in momentum as the driver hitting the windshield or flying through the windshield, and the impact time, the impact force, therefore, felt by the driver is reduced because of the equation force is equal to change in momentum over impact time. All right, let's move on. Alright, now question 5 says a 12-volt filament bulb is connected to a 12-volt power supply. Figure 6 shows how the current changes after the bulb is switched on. And so we've got the current on the y-axis in amps and the time on the x-axis in seconds. After 0.1 seconds, the bulb works at its normal brightness. What is the current through the bulb when it is working at its normal brightness? Okay, and so all we have to do is read off the graph. And at 0.1, it's here. So from here onwards, all of this, that is the normal brightness. And so where is that? Well, if this is 1.0, this is 1.5, that means each square relates to a value of 0.1. And so it's 1.5, 1.6, 1.7. All right, so the current is 1.7 amps. Okay, easy enough. Part 2, it says the bulb works at normal brightness for 30 seconds before it's switched off. Calculate the charge that flows through the bulb in 30 seconds before it's switched off and give the unit. Okay, so you should know that charge, okay, which we call Q, is equal to current times by time. All right, now charge is measured in coulombs, right? We'll come on to that in a second, but let's just fill in our units. The current is 1.7 amps. Okay, we've just worked that out. And the time is 30 seconds. So we do 1.7 times 30 will give us a total of 51. Okay, and that's 51 coulombs. And that is spelled C-O-U-L-O-M-B-S and a capital C for short. All right, so I'm going to say 51. And just to be safe, I'm going to say coulombs. You're told in the mark scheme that you could have wrote a capital C, but I would be careful because if you write a lowercase c, then you don't get the marks. All right, moving on. Part 3, it says calculate the energy transferred by the 12-volt bulb when it is working at normal brightness for 30 seconds and use the correct equation. All right, now we should know that the voltage, okay, can be written as energy divided by charge. And therefore, if we want the amount of energy, we can simply rearrange and we can times both sides by charge, and therefore we get that voltage times by charge is equal to energy. And if we just sub in those numbers, we get energy is equal to, well, the voltage was 12 volts, okay, times by, what was the charge over those 30 seconds? Well, it was 51 coulombs, and you do 12 times 51, and that'll give you a total of 612. And we don't need the units because they've given us that, so it's 612 joules is your answer there. All right, so 5b, it says between 0.02 and 0.08 seconds, there is an increase in both the resistance and the temperature of the metal filament inside the bulb. Explain in terms of electrons and ions inside the filament why both temperature and the resistance increase. All right, so first of all, we've got to think about the ions, okay? So the ions, okay, vibrate with more energy. So therefore, vibrate faster than they were before. Okay, vibrate faster. That's a result of kinetic energy, right? They've got increased kinetic energy, which as a result causes the temperature to increase, all right? That's because when you turn the bulb on, you've then got heat being given out, right? That causes the ions to vibrate more frequently or faster, okay? All right, so that's the first part. Now, why would that cause the resistance to increase? Okay, well, ions vibrate and impede the movement of the electrons. Okay, electrons' velocity or speed is reduced, which equals increased resistance, all right? Because resisting the flow of electrons is what resistance is, okay? Current is the flow of electrons, and going against that is resistance. That's what we call it, okay? And so that's enough for the 2 marks. So you've got to say that the ions vibrate, they vibrate faster. You can say that's a result of the kinetic energy. And you also have to say that the electrons are slowed down, or the electrons collide more frequently with those ions, and therefore we have a higher resistance. All right. So question 6. We are told that figure 7 shows the forces acting on a model air-powered rocket just after it has been launched vertically upwards, right? So we've got air resistance acting down, we've got the weight of the rocket itself acting down, but it's told us that the rocket is acting up, so there must be force acting up. How does the velocity of the rocket change as the rocket moves upwards? Okay, so there might have been some confusion, sorry about that. The rocket doesn't have any force acting upwards after it's been launched. So after it's been launched, the only force is acting downwards. So how does the velocity of the rocket change as it moves upwards? It will decrease to 0. All right? Now it will carry on after that, but it's asking us as it moves upwards, right? Because eventually it's going to move downwards. Now it says give a reason for the answer. And the reason for that is that the resultant force, and I'm going to put in brackets here, weight plus air resistance, is acting downward. Okay? Now we don't need to go into any more detail, but that means that you'll have an acceleration downwards because the resultant force gives you an acceleration. Alright, part 2, it says the velocity of the rocket is not the same as the speed of the rocket. What is the difference between the velocity of an object and the speed of the object? Okay, so velocity has both magnitude and direction. Okay, speed has only magnitude. Okay, so the difference between the two is the fact that velocity will include direction and speed will not. Alright, so 6b. So the speed of the rocket just after being launched is 12 meters per second. The mass of the rocket is 0.05 kilograms. Calculate the kinetic energy of the rocket just after being launched using the equation sheet. Alright, and so kinetic energy is equal to a half mv squared. So a half times m times by v squared. Now m is the mass and v is your velocity. And so that is a half times by 0.05 times by v squared. Well, v is 12, so square that is 144. And so you do have a calculator, so you do this in your calculator, and you'll get an answer of 3.6 as your total. Okay, so it's 3.6 joules, but they've given us the units, and so we just fill in 3.6. B part 2, it says, as the rocket moves upward, it gains gravitational potential energy. State the maximum gravitational potential energy gained by the rocket. Ignore the effect of air resistance. Now, a lot of people will panic on this question, but notice that it's only worth 1 mark, and that means you don't have to do any calculations. Kinetic energy is being converted here into gravitational potential energy. If all the kinetic energy is converted to gravitational potential energy, the maximum amount it can gain is the amount of kinetic energy you started with, which is 3.6 joules, and that is all you have to do. Alright, next, because we can't actually magic energy out of thin air, it has to come from somewhere, it has to be converted from one form to another, and that's what has happened. Alright, and so part 3, calculate the maximum height the rocket will reach. Ignore the effect of air resistance again, and we've got our gravitational field strength as 10 newtons per kilogram. Okay, so this time we use the gravitational potential energy equation. GPE is equal to mgh, alright? Mass times gravitational field strength times by the height. And so now we sub in our numbers because we know what the maximum gravitational potential energy is. It's 3.6. Is equal to our mass, which was 0.05, times by gravitational field strength, which is 10, times by our height, which is what we want. Okay, so I'll just carry on under. 3.6 is equal to, well, 0.05 times 10 is 0.5, and that's still times by h. To get h on its own, we need to divide both sides by 0.5. So we do that. H is equal to 3.6 divided by 0.5, and you divide by a half is the same as times in by 2, so you get 7.2, and that is in meters. So our maximum height is 7.2, and that is the answer. Alright, question 6 carries on, so we move on. B part 4, it says figure 8 shows 4 velocity time graphs. Taking air resistance into account, which graph ABCD shows the velocity of the rocket changes, how it changes as it falls from the maximum height just until it hits the ground. Alright, and so what we're looking for here is the fact that when something falls under gravity, gravity provides an acceleration, which means initially the velocity is going to increase. But that acceleration is provided in terms of its weight, and so the weight is the force acting downwards, okay? As the velocity increases though, air resistance increases as well. So as air resistance increases, okay, that means the resultant force on the rocket is going to decrease. When the resultant force decreases, that means that the acceleration decreases until the acceleration equals 0. Okay, and when the acceleration equals 0, you will have a flat line. Now what we've said there means that acceleration cannot give you a straight line, because velocity being constant means that there's no acceleration. There is acceleration, and so I'm going to discount A and I'm going to discount D straight away because they are not curves. Now, from what we said, the velocity is going to increase. Okay, that happens on both B and C. But the acceleration is going to decrease, and that means that the line is going from being steep to being shallow. And so in C, the line is going from shallow to steep, whereas on B, the line is going from steep to shallow. And so our answer is going to be B, because eventually you reach terminal velocity and air resistance has done its job, and you will flatten off. Okay, and so that's the answer to 6b part 4. C, we've got that the rocket can be launched at different angles to the horizontal. The horizontal distance the rocket travels is called the range. Figure 9 shows the paths taken by the rocket when launched at different angles. Air resistance has been ignored. What pattern links the angle at which the rocket is launched and the range of the rocket? And so we need to have a look at a pattern. Well, what's the best one? The best one is this one here, and that is 45 degrees, okay? You can see that when the angle, let's move up slightly, when the angle is 70 degrees, the range is quite short because obviously it goes up, but it doesn't go across too much. 60 degrees is slightly better, but it doesn't reach the range of the 45. Okay, and so that means that as the angle increases above 45 degrees, the range decreases. Okay, so that's the first thing I'm going to say. As angle increases above 45 degrees, range decreases. Alright, now what about at the lower angles? Because when the angle is less than 45 degrees, we also have a lower range, right? That's because you're shooting it too narrow and it can't get enough height to carry on going. It hits the floor. And the same with 20 degrees, it's even less. So, as the angle decreases below 45 degrees, the range also decreases, okay? So the range, so I'm going to say as angle decreases below 45 degrees, range decreases. Alright, and that is your answer. Now that actually brings us to the end of the entire paper, okay? So I hope you were able to follow that. If not, please just rewind and go through at your own pace. But that is the end of this video. So please do, as usual, like and subscribe because it really does help me out. But if you still have any questions regarding anything that came up in this paper, feel free to post in the comment box below. I'll be sure to get back to you, or send me a direct email using the link that is in the description box. But I look forward to seeing you in the next one.